Welcome to these lectures on algebraic geometry and commutative algebra. Last time, in the last lecture, I stated one theorem which said that Artinian rings are Noetherian, and I have not proved it completely. I have not even started the proof. So let us recall the statement and then we will prove it. So first of all, I have defined what is a Jacobson radical. So that was the recall that A is always our, let A be a ring, always commutative. Then we have defined intersection of all maximal ideals M in SPMA. SPM is the set of all maximal ideals. This we have denoted by M suffix A is called the Jacobson radical of A, and we have seen examples of Jacobson radicals of some rings, and also it is obvious that the nil radical Na, which is by definition intersection of all prime ideals, this is contained in the Jacobson radical. This nil radical is also the set of all nilpotent elements in the ring A, and this is also precisely the radical of the zero ideal. Also, one of the element wise characterization, like here nil radical is a set of nilpotent elements. So the Jacobson radical also one can describe like that. So I will write it as a small lemma. Let A be a ring then an element A belonging to the Jacobson radical if and only if 1 minus AB is a unit in A for all B in the ring A. So this is very easy to check. Let us quickly prove it. So proof. So first I am proving this. So I have given A is in MA, and I want to prove 1 minus AB is a unit for all B. If not, so if 1 minus AB is not a unit for some B in A, then we have proved as a corollary to Krull's theorem that every non-unit is contained in some maximal ideal. So then this 1 minus AB will be contained in some M, where M is a maximal ideal in A. But we know A also belongs to the maximal every maximal ideal, because A actually belongs to the intersection, and once A belong to M and 1 minus AB belong to M, then one equal to 1 minus AB plus AB. This will also belong to M, but that is not possible. So a contradiction. Conversely, this way, if I know that 1 minus AB is units for all B, then I want to prove that A is in every maximal ideal. Again, suppose A is not in some maximal ideal, for some M in SPMA, then, and I know that this is a unit, then this A is not in the maximal ideal. So, if I take the sum of M and the ideal generated by A, then I should get the whole ring A, because this A is not here. So, this ideal contains properly the maximal ideal, and therefore, it has to be the whole ring. So, that means 1 belong to that. So, that is 1 will be of the form C plus some multiple of A for some C in M and B in A. But now shift this B to the other side. So, that implies 1 minus AB equal to C, and these belong to this given maximal ideal M on one hand. On the other hand, this is a unit, that is what we are assuming, a contradiction. Since 1 minus AB is a unit, this is given. All right. So, that proves this lemma. So, that is element wise characterization of the Jacobson radical. All right. Now, let us come back to the theorem we wanted to prove. So, the theorem, this is very important theorem. So, let A be an Artinian commutative ring. This time I wrote in the bracket because mainly Artinian rings are studied mostly by non-commutative algebra people. So, I just wanted to be sure that everybody reads commutative here. Then we wanted to prove three things. One, the Jacobson radical MA of A is nilpotent. That means, so that is MA power n equal to 0, not for some natural number n. 2, the maximal spectrum SPM of A is a finite set. 3, A is a Noetherian ring. So, proof 1. I want to prove the Jacobson radical is nilpotent. See, this is more than saying that every element is nilpotent, because finitely generated ideals are nilpotent usually if the generators are nilpotent, but this ideal may not be finitely generated, that we do not know a priori. So, this is what we have to prove. So, all right. So, look at the descending chain. Since or maybe consider the descending chain. So that starts with A contained in MA, contained in MA square, and so on, contained in MA power n, contained in MA power n plus 1, and so on. So because we are assuming the ring is Artinian, that means every descending chain of ideals is stationary. So since A is Artinian, A is an Artinian ring, A is an Artinian ring, there exist n in n such that from this stage it becomes equal. From this stage it becomes equal. That is what we know from Artinian, such that MA power n equal to MA power n plus 1. And from here I would like to prove that m power n is 0. This is what we want to prove. Let us see how you prove that. I will first assume that m power a n is non-zero. Alright, so then we know this is also equal to m power n plus 1 is also equal to m power n times m. And now consider the set. Consider the set of ideals J. This is by definition all those ideals in the ring A such that m power n times A is non-zero. First of all, note that this is non-empty, since we have seen just above that M belongs to this family of ideals J. So therefore, again by using the Artinianness, we know that this family of ideals has a minimal element. So again, since A is Artinian, there exists a minimal element say B in this family J. Alright, so this B is the ideal in A and it is in this set. So that is m times m power, this is MA, MA power n times B is non-zero. But if this is non-zero, that means I can find. So therefore, there exists an element x in B such that MA power n times x is non-zero already, because if for all x in B this is 0, then that means this ideal is itself is 0. So this is also MA. Alright. So this is non-zero, but then therefore and hence by minimality of B in J, it follows that m power a n, so it follows that B is actually a principal ideal generated by X, because m a power n times Ax is already non-zero, and because X is in B, Ax is contained in B. So, by minimality it should be equality here. Alright, so we have proved that minimal element in the J must be a principal ideal. But now look at this. Now look at m power n, ma power n times m times Ax. This is ma power n plus 1 Ax, but m power n plus 1 is m power n times Ax, and this is non-zero. And this ideal now, this is a product ideal, and m a times Ax, this is contained in the principal ideal Ax, because ma is contained in A. So, this is also suffix A. So, therefore, further by minimality we get B must be equal to Ax, which is also equal to MAX, because this is smaller, therefore this has to be this. Alright. So, in particular, so what does this equality means? In particular, there exists A in MA such that you see X belong here and X is here. So, therefore, this X has to be a multiple of this X. So, such that X equal to Ax for some so, but this means what? Such that this equal to equal, because X belongs here, so it is this, but this equation means, so that is X times 1 minus A is 0. But what is A? A is actually in MA, so it is in a Jacobson radical. So, A is in a Jacobson radical, and just above we saw if some element is in the Jacobson radical, 1 minus that element has to be a unit. Therefore, this is a unit. So, that implies, so I write in the next page. So, since A belongs to the Jacobson radical, 1 minus A has to be a unit by earlier lemma. And then X has to be 0. So, because what we have equation is from 1 minus Ax is 0, we get, you multiply by inverse of 1 minus A which exists, we get X equal to 0. but x were a non-zero element. So, which is a contradiction. Therefore, what we proved is we proved what wanted. So, I will show you. See, we wanted to prove that m power n to be 0. So, I assumed it is non-zero and we got a contradiction. So, that means we have proved that m a power n is 0. So, that means, so I will write here, this proves that m a power n must be 0, that is m a is nilpotent. This proof is not so difficult, we only have used essentially the definition of Artinian rings. Okay, so second is what assertion? Second assertion says that the set of maximal ideals of A is a finite set. So, to prove that the set SPM A is finite, this is what we want to prove. So, consider so also note that before I start proving this is a finite set, note that distinct maximal ideals in a ring are co-maximal. So, I will just recall for convenience the definition of co-maximal. So, two ideals A and B in the ring A, ideals in A are called co-maximal if their sum ideal is the whole ring. In other words, there is no maximal ideal M in A which contain both ideals A and B, because if some maximal ideal contain both, then it will contain their sum also, but the sum will not be the whole ring then. Okay, so these are the co-maximal, and so if you have two maximal ideals M and M prime, two maximal ideals M not equal to M prime, then therefore M plus M prime, this has to be the whole ring A because it contains properly M, because M is different from M prime. So, that is what the assertion above I made. Alright. So, if I take different maximal ideals, they are co-maximal. Alright. So, now start with any maximal ideals. See, I want to prove that there are only finitely many maximal ideals. So, let start with any M1 to MS in SPMA be distinct maximal ideals, and consider the chain, descending chain again, because that is the only tool we have in the hand. So, A not equal to M1 containing not equal to M1 M2 contained in not equal to and so on, contained in not equal to M1 to MS. I have written it, but I have to justify why these are proper containments. Alright. This chain is a proper, it's a descending chain, then the descending chain is strict at every stage, at every place. Why is that? So I have to justify that no matter what I take, they are inequality. That is because they are all ideals in the ring A. So I want to show that, look at this M1 intersection MR. So R is any number between for 1 R equal to 1 to S. We have this intersection is properly contained in the next intersection. Maybe you have to take only up to S minus 1. So I will make it more clearer here. 1 less equal to R less equal to S minus 1. Alright, why this properly contained in? Because this follows from the following. If so, this first of all note that co-maximal ideals, for co-maximal ideals intersection and product is same. So this is, since one reason is note that co-maximal ideals A and B, A intersection B is same thing as AB. This is easy to check, so I will just say check. That is one reason. Also we have to use the fact that if A1 to AR plus 1 are pairwise co-maximal, which is the case we have, MIs are pairwise co-maximal, then in A, then if I take the intersection of the earlier ones, A1 intersection AR, and along with AR plus 1, these are two ideals, they are also co-maximal. So in particular, if I take the intersection with this, this should be properly contained in this. This is very easy to see from the co-maximality here, because if this is equal to this, that means every maximal ideal which contain this intersection will also contain this. But that is not true, because they are co-maximal. This one is also easy to prove, that because if a maximal ideal contain the product, then it will contain one of them and then it will not contain the other. Therefore this is proper, but that is also the product. Therefore we check that, so therefore the strictness in the above descending chain is clear because of this reasoning. Therefore, since A is Artinian, A is an Artinian ring, it follows that SPM must be equal to M1 to MS. Because if there is one more, then I will extend the descending chain by one more at least. So, it will not go on forever. So, at some stage it will stop. That means that the chain will involve only finitely many. If this set is not finite, then I can choose arbitrary many maximal ideals and keep writing the chain, which will go on for long time and which will not be stationary, and therefore, there has to be finitely many maximal ideals. Alright, so we have proved second also. So, this proves assertion 2. Now, let us come back to the proof of 3. Now, we know that the maximal spectrum is finitely many finite, and also I know that this MA, the Jacobson radical, is then intersection of this M1 intersection MS. This is nilpotent by 1 by 1. Therefore, when I raise power n and this power n, so therefore, it follows that 0 must be equal to the product of maximal ideals. With maximal ideals N1 to NR. Note that I have used a different letter because when I raise it to the power n, this will be power n. So, many of them will be repeated. So, some of them may be repeated. So, therefore, they are same. I have written the different letters. So, since I would say since M A power n equal to M1 MS whole power n, this is 0, because this is intersection is same as the product because they are co-maximal, and therefore, when I expand it, you get a product of maximal ideals. I do not care how many times they are repeated. So, alright, so therefore, now 0 is the product of maximal ideals. Now, I am define. So, note that the ring is Noetherian. So, I want to prove. So, to prove that the ring A is Noetherian, I will consider the chain of submodules and successive quotients. If are Noetherian, then the whole. So, okay, let me write it first and tell you. So, alright. So, if I look at the residue class module. So, I know that N1 to NR, this product is 0. From here, I put Vi equal to N1 to Ni. This I put it for I equal to 1 to R, and I consider actually this Vi, I do not put this, Vi I put the product up to I minus 1 modulo the product N1 to Ni. This makes sense because this is contained here, and now this Vi is this residue class module. Think of all these are modules over A, therefore the product and they are ideals, so therefore they are modules over A, and Vi is this residue class, so this is a AI module, A module. In fact, Ni of V, if I multiply V by Ni V, then Ni will come in the numerator, so this will be 0. That means Vi is annihilated by Ni, therefore actually Vi will actually be, Vi is A modulo Ni module, because it is annihilated by Ni, therefore it has a module structure by A modulo Ni. So these are the modules which are actually vector spaces. So these are vector spaces. Vi's are A mod Ni vector space, because we use this is a field, therefore modules over a field we are calling vector spaces. This is for every I from 1 to R, and therefore Vi's are Artinian because they are finite dimensional. These are the residue class modules. No, Vi's are Artinian, A mod Ni modules, since they are residue class of the submodules of Artinian is Artinian, and the quotient modules of Artinian is Artinian, therefore Vi's are Artinian. And Vi's are A module structure and A mod Ni module structures are same. So therefore Vi's are Artinian modules, therefore Vi's are also Noetherian. A mod Ni. See, they are vector spaces. So this is vector spaces. For vector spaces, Artinian, Noetherian and finite dimensional are equivalent. Now these are successive. We have a chain. So you start with A contained in N1, contained in N1, N2 and so on, and finally you go on to N1 to Nr. This is 0 we know. So we have the chain, and the successive quotients are Artinian modules, and therefore they are also Noetherian because they are vector spaces. Therefore this is 0. So start, this is 0, so this is Artinian, this is Noetherian, then this is Noetherian, this is so. So that proves that, this proves that A is a Noetherian A module, and hence A is a Noetherian ring. This is what we wanted to prove. So we have finally proved, we completely proved the theorem, and now after the break I will also do very important lemma called Nakayama lemma, and I will digress it by the minimal number of generators and so on. So thank you. We will meet after the break.